This is lecture 27 from Fundamentals of Surveying, and this is the second and last lecture on the topic of vertical curves. If you remember, in the last lecture, we used the general equation for the parabola, which has been modified for our purposes so that y equals the elevation on the curve. A is 0.05, which is big A, G2 minus G1 divided by 2L, which is 600 in our case, because this is the same example from what we worked on the last lecture, where L was 300, so times x squared, and then minus 0.032x. Now, if you remember, this is plus bx, but it turns out this is a negative grade, so I've just gone ahead and changed the sign in the equation itself. And of course, the 470.72 stands for the C, and we created this table. One of the things that happens is that when you are asked to calculate a vertical curve, it's almost inevitable that you will have to determine the location of the high or low point. And when I say location, I mean the stationing, and then we often say the location and the elevation of the high or low point. Now, what do I mean by the high or low point? Well, there cannot be a high and a low point, and so we often go to the curve to inspect it to figure out that in this case it's a low point and not a high point. Now, one of the things to remember is that if we have a descending grade and then another descending grade like that there's no such thing as a high or low point, because the parabola that fits in here kind of goes off into space. There's the beginning and end of the vertical curve, but there's a low point that's way off to the extreme right beyond the edge of the board. And similarly, we can construct a parabola that goes the other way that would also have a similar situation. So high or low point where we have a G1 and a G2 that are the same sign does not mean anything. So you have to have opposing signs so that you can have a low point in this case, because we have a minus G1 and a plus G2, or the other way, you would have a high point, a plus G1 and a minus G2. So I just wanted to make sure that you're aware of that, and it's a good idea to actually inspect it by drawing a rough sketch that's at least accurate in terms of positive and negative grades. So where is the high or low point? Well, it turns out if you're using the equation of the parabola, it's where you have zero slope at the high or the low point. So if you take the derivative of the parabola equation and set it to 0, we get this location, meaning the location of the point we solve for x, and it's equal to minus G1 times L over A. So if we go to our curve here, we have minus G1 times L over A. So we have a minus negative 3.2 times 300 divided by 0.05. Turns out to be 192 feet. So in terms of stationing, that's 1 plus 92. So the stationing of our low point would be 28 plus 80, which is the beginning of our vertical curve. And then we add the 1 plus 92 to get 30.72, or 30 plus 72 for the stationing of the low point on the curve. So one of the things that you can do then is, once you have the x, meaning the stationing measured from the distance, horizontal distance from the beginning of the vertical curve to the zero slope point, you can then substitute that number into the curve equation to get the elevation of the high or low point. So, surprise, surprise, here's a little quiz for you to work on. I'm going to pause the video so that you can take this data, I have it summarized on this slide here, and use it to solve for the elevation of the low point. So hopefully you can be successful in getting to this point. So remember, the stationing of the low point is at 30 plus 72. The BVC is at 28 plus 80, so we subtract one from the other to get 192 for the distance. When we substitute into the equation for the elevation of the curve, let me bring up my calculator. So we have 0.05 over 600 and we multiplied that by x squared, and x is 192 feet. So we get 3.072. Then we do the next part, which is 0.032x. So 0.032 times 192 equals 6.144, but it's a negative number. And then we're going to add the 470.72, which is C. So if we sum all of these together, and I'm just going to take the 6144 that I already have in my calculator and change it to negative, then I'm going to add to it 3.072 and then add to it 470.72 to get 467.65, and that's what I have here. So hopefully you got that as the correct answer. I've written down the intermediate values on the slide so you can see what they are. And it's a really important part of the problem solving. Now, why should you care about the high or low point? As an engineer, when you design highways, you are constantly worrying about clearances. In a couple of different ways, you're also worried about drainage. So let's look at the low point situation. When you have a low point situation, you need to know where the low point is, because very often your storm drains will come together there to pass water under the road perhaps. So it's a very critical thing to know where the surface of the curb is going to be, or the surface of the road is going to be, to make sure that you know where to put the storm drainage collection system. And if you have a pipe that goes through the road, through the fill here, or underneath the road, there's also things having to do with clearance. You usually have to have so much cover over the pipe. This might be a function of the material that the pipe is located in. It might be a function of the shape of the pipe, might also be a function of the size of the pipe, and of course the loading that the road may encounter with traffic passing overhead. So very often, as part of the design process, this is not directly a surveying problem, but as part of the design process, an engineer would locate a pipe that goes underneath the low point at a certain distance below the driving surface. And then from a surveying point of view, the surveyor may have to come in and actually provide control, vertical control, to enable the contractor long before the road is built to make sure that the pipe is located in the right place, and also that it's sloping in the right direction and with the correct amount of slope to make sure that the water flows through from right to left or left to right, depending on which way the water is going to get taken away. When you have a crest curve like this, one of the things that happens when we put the curve in is we often worry if it's what's called a grade separated intersection. In other words, when two roads intersect, rather than intersecting at the same elevation, one is raised or lowered compared to the other grade. That's what grade separated intersection means. And so if we're going to have a bridge up here, and I'm drawing it in this plane, but the bridge may be coming in and out of the plane of the board, maybe not at right angles, but at some other angle, we want to make sure that we first account for the bridge structure, whatever that is, and that if we then have a truck or something like that, that the truck actually is able to clear the road, clear the height clearance that is specified for that particular road design. And so very often engineers will need to calculate if the road that they're passing under already exists, they may have to work backwards and figure out what G1 and G2 may need to be, so that they can have a good transition or design a length of curve that's long enough to bring the driving surface down and so forth. So there's a whole bunch of variables that people who do the geometric design of the highway as opposed to the surveyors will have to do. But I just wanted to point out why it's important to know where the high and the low point are, because very often the surveyors then have to verify some of these things, because it's not uncommon for a theoretical calculation to be done. Surveyor goes out in the field and discovers somebody made a mistake, and there's only 3 feet of clearance, so there's 30 feet of clearance, which is way more than is needed, making something perhaps a lot more expensive than it needs to be. So there's all kinds of issues associated with vertical curves that engineers who do the design of the highway, the geometric design of the highway, need to work out. And it's good for these people doing the surveying to be aware of what those issues are that they're working around, so that they can actually point out if there's perhaps a miscalculation that has occurred. It's probably a good time for me to just mention that it is quite a few times that surveyors will discover mistakes made by others. So that could be a contractor, that could be an engineer, that could be an architect, where they assume something, the surveyor goes out and tries to lay out the structure, because that's the first, if you will, realization of the design in the real world, and will sometimes discover that things aren't working. So it's a really important thing for surveyors who are doing this kind of stakeout work, this kind of layout work, to actually understand some of the nuances in the design part, so that they can actually verify or confirm that the design is holding up. All right, so some parting words before we go away. Not all textbooks use the same terminology. I've said this over and over again with other topics here in this course, but in vertical curves, some of the variations that happen is that L, the distance L, rather than being in feet, and X, rather than it being in feet, will be in stations. So you remember we had 192 stations, 192 feet, but we might actually put that in as 1.92. That's almost always the case when the grades are put in percent rather than pure numbers. So if you remember in this particular example, A was 0.05, and in that particular case, it's a variation. I'm not saying you do it unless you make all these changes. You would use 5 instead for the percent grade. The names for the beginning and end of the curve and the grade intersection have huge variability. I've seen quite a few ways that different textbooks indicate it. That's not such a big deal. As long as you speak English and you understand the terms, you can usually figure it out by reading the introduction to the vertical curve segment. And then you may remember in an earlier slide, last lecture, I talked about the term R, which is G2 minus G1 over L. Well, G2 minus G1 over L is A over L, and it turns out that if we have this expression A over 2L, if you remember that was A, small a, in our general curve equation, So that becomes R over 2. So just be aware that different people combine some of these terms differently. It turns out the term R kind of comes from the railroads, because railroads are typically, or trains are typically extremely low power. So they have some limitations on how high they can go pushing or pulling a train that's heavily loaded. So very often the railroad engineers need to figure out what's called the rate of change of grade on the entire curve, and that's where the term R, and that's why the letter R is used. It stands for rate of change of grade. And so that brings us to the end of vertical curves. Hopefully we've covered enough of the example calculations so that you can work out a few problems.